Right, class. Welcome to another session on introduction to heterocyclic chemistry. Now, want to look at stability of uh, ring systems. As you know, heterocyclic molecules, you're dealing with ring systems in which at least one atom in the ring is a heteroatom. It means a hetero means you're talking about an atom other than carbon. If all the atoms were carbon, then we'll be talking about a homocyclic. But now we're talking about heterocyclic, and in this course, the common ones we are going to be studying are the ones containing nitrogen, oxygen, and sulfur only. There could be other atoms like silicon, phosphorus, and the rest, but that's going to complicate. So we're just going to restrict ourselves to the three atoms: oxygen, sulfur, and nitrogen. Now, when we're talking about stability, then there are uh, uh, it can be said that if you're dealing with saturated, the ones which do not have double bond, then there is an aspect of ring strain comes into effect. I'll mention that one later. And then when you're talking about unsaturated ring systems, then we'll be talking about either a ring system being aromatic or non-aromatic. It means that you're not having 2n plus 2 pi electrons, or on the other side, you could be talking about something which you call anti-aromatic. It means that you've got a 4n number, so that you'll be talking about 4 pi electrons in a ring, or 8 pi electrons, 12 pi electrons, and the rest. Yeah. So such ring systems are said to be more unstable than the open ring system, but aromatic systems are going to be stable. So let us look at saturated systems. Now, the ideal bond angles are a tetrahedral, whereby the bond angles are going to be 109.5. Yeah, you've seen a tetrahedral system. I think I'll be able to show one later. I think, or maybe I can just show. Okay. Let me just get a simple system. Yeah. So in a tetrahedral, we're talking about yeah, the bond angles being 109.5. Each of these was this is an example of a tetrahedral system, and in a cyclic case, uh, these bond angles are found in a cyclohexane. It means that it is cyclic and it is six-membered. So all the bond angles are 109.5. Now the next best one is a cyclo pentane, and just wanted to give example of a case whereby um, let's say like I'm just trying to form a ring system. In this case, let's say the red atom is the heteroatom. In this case, I want to form a five-membered ring. Yeah, I mentioned the most ideal is a six-membered ring. So in the five-membered ring, the bond angles are less than the ideal one of 109.5. But in this case, you're going to see that if I'm just going to form a ring system, uh, though there is some strain, but not much, so it is easy to form a five-membered ring. Now, cyclobutane, four-membered ring and a three-membered ring are usually unstable. And I just wanted to give an example of, in this case, I want to try to form something like a three-membered ring. Now, what I've done is that I've chosen long long bonds compared to like the slightly shorter ones which I had earlier, because in this case, if I just try to make, I'm just going to really like do like bending. It's not easy. So you're going to see that trying to form a three-membered ring, like in this case, I may try to like destroy this structure, but uh, if I just try to force, oh no, this one is actually bending, but I just try to give an example of like in this case, oh, you can see this one is bending, but trying to form a three-member ring whereby the bond angles are 60 degrees. Now this bond just had to break because three-member rings are usually very strange. So does that tell you? Yes, you can try to form a three-member ring, but they are going to react very quickly. So when you're going to be dealing with a three-member ring and four-member ring, please remember, class, as much as you may try to form, they are very easily broken, and you're going to see the conditions under which you can easily break a three-member ring, three and a four-member rings. Yeah. So uh, uh, four-member ring and three-member rings are usually unstable and strained, so they are quite reactive. Okay. Now going to the unsaturated. Uh, uh, so the thing is, okay, let me just say, sorry, 4n plus 2, yeah? So that in this case, we'll be talking about the pi electrons being, in general, 6, 10, and the rest, yeah? You'll be talking about that aromatic number. Sorry, I put different number earlier, so it was a typographical error. So the most stable for the aromatic, excuse me, we'll be talking about six-membered ring like a benzene, or if you're going to add a heteroatom like nitrogen, then you're going to have something like pyridine. So in general, in the six-membered ring, the bond angles are well optimized. But I just want to mention something about five-membered ring. So talking about a five-membered heteroatom in which uh, the heteroatom forms part of the aromatic ring. Yeah. So in this case, we can say that if you're going to add in, just to give an example here. Okay. 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 This was initially for this saturated. Yeah. But if it was unsaturated, it means that instead of two, you're going to have one hydrogen on each carbon. Yeah. So the bigger the group, then the more wider the bond angle. So that in this case, I'm going to say the sulfur will be more aromatic, and the way you're going to have an oxygen atom which is quite smaller than nitrogen, then the bond angles are going to be quite strained. So the more strained it is, then the less aromatic, the less stable it's going to be. So in general, thiophene, by the five-member ring with a sulfur will be more stable than for pyrrole, and also then there will be the what, um, but not much difference between thiophene and pyrrole, but for what do you call it? But for furan, which is the last one, I think you're going to get the lowest aromaticity. I think I wanted to see. Uh, uh, I wanted to see the page number. I think according to this one, it's under aromaticity index for monoheterocycle. So you're just going to see that one in your notes. Yeah? Um, so there's the thiophene, then there is the pyrrole, and then the last one there, excuse me, on that part is the furan. So um, I think that's the much I'll talk about the stability of the ring systems. We talked about saturated and we talked about unsaturated. So I think want to look in a short while the what do you call it? Uh, uh, Particularly the what do you call it? uh, the attack of the nucleophile on the especially on the saturated ring system, how it actually opens up. Yeah, want to look at some of those reactions so that you'll be able to answer some of the questions related to the reactions of saturated ring system. So I'm just going to pause a bit. I'm going to pause. I'm going to stop, and then I think it will be under a new lecture on the ring systems reactions with nucleophiles. So I believe you've learned something about saturated and unsaturated ring systems, and that the ideal bond angles are at tetrahedral angles. And in this case, uh, the ideal system is where you're going to have uh, a six-membered aromatic system like which you're going to call like pyridine. Pyridine, you're saying it's like you have what? It is similar to benzene, but there's a heteroatom. In this case, it is nitrogen. So that's an example of a pyridine. It's a six-membered ring with six pi electrons. It's aromatic. The bond angles are ideal. It has the least strength. So let's stop there. I think in a short while we'll look at other reactions. Okay, thank you.